What we discussed 2 weeks ago, I discussed about the effects of zeros and additional ports and stability criterion Rutherford's. Last week, I briefly talked about the basic equation of control. I will continue this concept today. And for the next week, I will talk about the control of steady state error. I will talk about the system type today as well. And for the control of dynamic error, PID control, I will talk next week. We talk about it, what is the benefit and advantage and disadvantage of having a feedback or closed loop control system compared to open loop system. What are the advantages of having a closed loop system or feedback system? What are?
Handles disturbances better.
Yep. Disturbance rejection. Robustness against parameter variations. A stable system, stabilizing if the system is not stable. Okay, and better tracking, reference tracking. So I will quickly pass this. Here is the advantages and the disadvantages. We have two problem or two issues with the feedback systems. One is the design is complicated compared to the open loop system, and the second one is concept. Yes.
Is this from last week?
Yeah, it's from the last week. I'm quickly reviewing. Okay, for the open loop system, if you see here is the block diagram of the open loop system. We have a plant G, we have the controller DOL, open loop, and we have the input shaping HR. What was the input shaping block? Why do we have the block shaping? I talked about it last week. Just reviewing.
To change into like electronic.
Exactly. Look, the dimension of output and input, reference input, we talked about it, is the same, should be the same, because we are looking for the difference of these two variables in the case of the closed loop system, or in the case of open loop system, we want to have the response close to the reference input. So they should have the same dimensions. But usually the input to the controller is the voltage, is the electrical signal. We need to have some device that convert the mechanical dimension to electrical dimension. Mechanical dimension can be angle, can be displacement, can be velocity, can be acceleration. The input to the electrical system or device usually is voltage, or in some cases is ampere, current signal. Right? So we use block HR as a block diagram of a device which converts the mechanical signal to electrical signal. Okay? But as we discussed last week, the most important for us is the error between the output and input signals. The objective of a control system is that we have the response close or exactly the same as our desired input, which is the reference input. In order to have the some sense, is the response close to our reference input, or is it or not, we need to have something to as a baseline. The best thing is error, the difference between the output and the reference input. For the feedback system. For the open loop system, we don't have any measure of the output in order to compare to the response input. We try to design our controller for the specific or for the certain conditions such that give us the response close to the reference input. But if the parameter change, if some disturbances happen to the system, the open loop system cannot handle these situations. So let's calculate the error for the system. Before that, we assume that we have a disturbance to the plant. Disturbance can be any signal, but disturbance is unwanted signal to the system, undesirable signal to the system. And we, in order to have as response close to the reference input, we need to reject or reject the effect of this signal from the output signal as much as possible. Okay? How we can calculate the output? The output of the open loop system is combination of these two responses. Why? Why the output is in this form?
Because they're in series.
Because of?
Series, they're in series, the boxes.
No.
Because there's effectively two inputs.
Because of?
Effectively two inputs with the disturbances.
No. Look at inputs. How many inputs do we have here?
2, 1.
2 inputs. For a linear system, if we have 2 inputs or multiple inputs, how we can calculate the overall response of the system? Superposition principle. Exactly. So here, look, I have 2 inputs. So my final response is composed of 2 responses. One response due to the reference input and one response due to disturbance input. Correct? In order to calculate using the superposition principle, I first assume W is 0. Ignore disturbance. So the transfer function from the Y to R will be the multiplication of these 3 blocks because they are in series. Correct? Which is HR, DOL, and G. The second response is due to or because of disturbance input. So I put R equal to 0. The only block is between W and Y is plant G. So the response because of the disturbance will be GW. Y over W is G, so Y will be GW. Here, Y over R. Y over R is this multiplication of these 3 series blocks. So Y, because of the reference input, will be HR, DOL, G, R. This is for the open loop system. If I want to calculate the error, what is the definition of the error?
Difference between output and reference.
Exactly. The difference between the reference input and the output signal. So the mathematical presentation of this error of the open loop is R minus YOL. R is the reference input, YOL is open loop output response. R is the reference signal, but we calculate the output of the open loop system here as the summation of the response because of 2 inputs. Here in the response I have R. I factor out R or reshape this transfer this system. I will have 1 minus HR DOL G multiplied to R minus GW, or 1 minus trans function of the open loop multiplied to R minus GW. If W is 0, the response will be only this. The error will be because of the reference input. If the reference input is 0, the error will be just because of the disturbance input. Correct? Any question? Yeah?
Why is not YOL minus R?
R minus YOL. The difference from reference input and output response. Yeah? Why it is? Why we define error such that? Because we want to have the response close to desired input or desired response reference. If error is 0, it means we have exactly we want. If error is not 0, we need to see how much deviation our response has compared to the reference input.
So YOL is always greater than R. I mean,
It's not.
Less than R.
No, it's not. Not always. If this is the standard definition, okay? If error is negative, it means that our response, if we have the constant input, in the case of the constant input, we have the response lower than reference signal. If it is positive. If it is negative, our output is higher than our reference input. But if we have this random input or non-constant input, we can't say. We just look at the sign. If there is minus, it means that we have the higher error. If it is positive, it means that we have less than the reference signal. But this is a standard definition. We define as the R minus Y OL. It doesn't mean necessarily the output is smaller than input. Okay? But the desired error, we want to make error equal to 0 in order to have the response close to our reference input. You have a question?
No.
Okay. For the control system, feedback control system, as we discussed, we have a plant, G. The plant can be any application. Suspension system of vehicle, can be cruise control of the automotive, can be Mysol, control of the Mysol, can be anything. Anything that you want to have a perfect response from it is the plant. But in order to control the plant using the feedback system, we need somehow to have information from the response of the system. How we can get information from the response of the system? Using sensor. Correct? So we need to use the sensor to measure or get information from the output response of the system. Here is the output. We use the sensor to measure it. I show the block diagram or transfer function of the sensor by HY. Again, we have the reference input. This reference goes to the input shaping block. And here we have the summing device. And the difference from the reference input and the output from the sensors build the error signal of the system. The error between the output of the sensor and the reference input gives you error signal, and the error signal goes to controller. And controller tries or need to function such that make the error 0. So it adjusts the input to the plant or generate a control signal U such that the error goes to 0 during a finite value of time. Is that clear, the concept of the control system and feedback control system? Why we design feedback? Is any question? Is it clear to everyone? Good. But the point is that as a disadvantage of the feedback control system, if we use the sensors have some noises. Add noises to the feedback system, and this noise maybe deteriorates the response of the system or the performance of the closed-loop system. How we deal with this one? We talk about it. And we have the W, the disturbance to the plant. Again, disturbance is unwanted signal, and we have to reject its effect on the response, final response, as much as possible. To mathematically model this system, I put the input as a summation, the disturbance input as a summation to the control input, and disturbance or noise V as a summation to the input of sensor. Mathematically can deal with this one. Okay, in this block diagram, how many inputs do I have? 3, which are reference input, disturbance input W, and the noise input, sensor noise input V. So the final response of mine, or final response of this block diagram, is composed of how many? 3 inputs. So my transfer function needs to have 3 components. Or the final response is composed of 3 transfer function to associated input. How? Okay, what happened? Okay, something is gone. But anyway, I will to discuss to the next slides. Okay. In general case, sensor is a dynamic device. As a dynamic device, we have one input, one output. The input is the output of the plant, and the output of the sensor is what has been measured. But in reality, sensors are very accurate. In a special case, if they are very expensive, they are accurate and they are fast. So you can ignore the dynamic of the system and consider it as a static system. What's the difference from the static system and dynamic systems? As a third year mechanical engineer,
Nothing changes in the static system.
when nothing changes in the static, what does it mean? As a mathematical point of view,
Constant.
constant. You have a constant. You can show the performance of the system by a constant value. When you have a dynamic system, you have variation, and your response and your system states will change based on time. So you have a differential equation. You need to represent the performance of the system by differential equations. But in a static system, there is no differential, just a constant gain. In sensor case, because we have fast and accurate system, we can just consider them as a constant system. As we discussed, the output and input of the system, closed-loop system are the same, but the output and input of the sensor are different. The input is usually displacement, displacement, acceleration, velocity, angle, whatever you want to measure, and the output will be voltage. So the unit of the gain will be volts per unit of output of the system. And the same for the shaping block. I can summarize or reshape the closed loop system. Look, in my case, I have HR, shaping block, summation, controller C, plant G, controller D, plant G, HY, the sensor, and here. Okay. Based on the second gear control module, if you have a system H, block H, before the summing point, you can bring H in front of summing point by some calculation. So in fact, I can remove this H block to the front of summing point by reshaping as this one, H 1 over H. Okay? So this block diagram is equivalent to this one. If you look at the second or third lecture of the Year 2 control module, or if you look at your lecture notes, for sure you can see this one. But let's assume this one is correct. If I have a block behind the summing point, I can move it to front of summing point by adding these two blocks, H and 1 over H. 1 over H in the feedback and H in feed forward path. If I do this way, I can simplify my block diagram as shown here. HR and this closed loop contour gain, and here HY, which is the H of the sensor divided by HR. Look, here I bring HR in the front. If I want to bring it in the front of summing point, I will have HR here, and the one H1 over HR here. So HR multiplied to HY makes H, and HR multiplied to D makes HR DCF. which I choose as the control gain and here as the feedback gain, H. In reality, both HR and HY are constant gains. And it is proper to have the good control system design. It is practical to select HR equal to HY. Okay? If I select HR equal to HY, this ratio will be 1. HR over HY will be equal to 1 because HR is equal to HY. Then I will have a unit feedback in my feedback path or unit gain in my feedback path. The reason we choose the HR equal to HY is to make the system unit feedback. And the controller will be HR, the closed loop or the controller. If HR is 1, which is not the case, D will be equal to D closed loop. And we have plan G. In this lecture, just in this lecture, I will develop the equations and transfer function for this standard unit feedback system. Okay, just in for this lecture. I will discuss if in the case HR is not equal to HY or is not possible to choose HR equal to HY. Okay, but in this lecture, I just talk about these unit feedback systems. Okay, so if I have this unit feedback system, I want to build up the relations between 3 inputs that I have, W, V, R, reference input R, disturbance input W, and sensor noise V, based on the defined relation for the error. Again, the error is what?
R minus 1.
R minus Y. In this case, Y closed loop. So in order to build up the error of the system, I need to calculate Y of the closed loop based on these 3 inputs. I have 3 inputs, R, W, V. Based on this superposition principle, to calculate the transfer function from the Y closed loop and R, I put W and V equal to 0. If I put W, V equal to 0, in feed-forward path, I have D and G. And the closed loop path, I have a unit negative feedback. So the transfer function is dg over 1 plus dg. Now I put R equal to 0, V equal to 0, I have just W. What do I have in the feed-forward path? Look at from W, W is your input, Y is output, D and R are 0. What do you have in your feed-forward path? Just look from W to Y. Just plant G. Okay? And what do you have in negative feedback? Look from the Y to this summing point. You have controller D. You have a minus here as well. So in fact, you have minus D. This minus will be multiplied to this D. You will have G in the feed-forward path, 1 plus dg. Yeah. I think I have a mistake here in here. It should be minus dg. Oh, no, it's correct. So minus dg, if you look at this, your transfer function will be 1 minus dg, minus by minus will be positive. So it's correct. So we'll be g over 1 plus dg. Now we are looking for v. put W and R equal to 0. From V to Y, what do you have in feed-forward path? DG minus DG. You have a minus here as well. Minus DG. And in the feedback, from, look, if you, from the V to Y, and from Y to V, you have a positive feedback. So minus DG over 1 plus DG multiplied to V. This is the overall closed loop response of the system because of 3 inputs. Any question?
You notice 1 over minus dg, is that for all of them, or is it just one of them?
Look, we have, if this is positive, negative, assume here I have dg. Let's say here is the output. What will be transfer function? 1 over 1 plus dg. Sorry, dg over 1 plus dg. Correct? Now let's look from W to Y. From W to Y, if I rotate signal W, here is W as the input, and here is the summing point, plus feed-forward path, I have the plant G, the output Y. Correct? Is that clear to everyone? Everyone clear? Good. In feed-forward path, what do I have? Positive, positive. So nothing will change. If I come here, this one is 0. The output here will be negative because something 0 minus something. So this minus will be multiplied to this. I will have a minus D in my feedback. But positive here. I said if we have negative, positive feedback, the transfer function will be dg over 1 plus dg. If it is positive, positive, it will be dg over 1 minus dg. Correct? So if you look at here, dg, okay, but here d is in feedback loop. Keep in your mind. So the transfer function here will be what? G over. I have positive, here will be negative. 1 minus d multiplied to g. So it will be equal to g over 1 plus dg. Correct? If you do for the from V to Y, you will get this way. From D to Y, this is signal V. I have positive, 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 positive. If you look at the from feed-forward path, I have dg and minus here, so it will be minus dg. Here I have minus dg, the output 1, and here I have a negative, positive feedback. Again, I will have minus dg. Here I have positive, so I have negative in feedback, minus over minus dg. So it will be equal to minus dg over 1 plus dg. What I have here. Okay?
Sorry, could you just explain once more why it's minus dg. I know there's something to do with the negative
Look, let me
summation.
explain the general case. If I have D, G, H, here, positive, negative. If it is positive, negative, the closure transfer function T will be dg1 plus dgh. Okay? If it is positive, positive, the transfer function will be equal to dg1 minus dgh.
It was when you changed dg on the top,
It was when
combined
DG
it to minus dg.
Okay. If look at the from V to double, from the Y to V.
Yeah.
Okay. So if you look at from Y to V, what is in your feed forward path? Look at start from V after summing point. The first thing you will see is minus. Minus goes to D, so I will have minus D. Then you need to ignore this one because W is 0. Positive, positive. Minus D, then multiply to G, I will have minus DG. So in the here, I have minus DG. If you look the feedback loop from Y to V, positive, positive. So this summation is positive, positive, and I have a unit feedback. So H is equal to 1. So the overall closed loop system will be minus dg, positive, positive, here V, Y, unit, positive feedback. Just a moment. Minus D comes from here, from this summing point. You are looking from transfer function Y over V. Correct? Yeah.
So the minus dg, the minus is come from that.
This summing point, yes.
Plus times minus.
Yeah. Minus multiply to D. Look, when this R is 0, you don't need to look at this part. You just look at the path. Okay? Any other questions? Any question? Good? Good? Okay, so let's continue. As a practice at home, find the transfer function between u and y. If I want to calculate u, I need to have these relations. The principle is exactly the same as this one. But I leave this one to you in order to have some fun at home. Okay? It's not a big deal. If you have any question, come to me, ask me. Okay? So, again, the most important thing in feedback control system is error. We want to make error equal to 0 in order to have Y closed loop equal to R. Our closed loop response close or exactly the same as reference input. If I build up my closed loop error, which is the difference from the reference input and output of the closed loop system, I will have these relations. R is the reference signal, and here, this in the bracket is the Y closed loop. Closed loop system. We calculate the transfer function or the system, the response in S domain in the previous class. If again I reshape or simplify this relation, R minus dg over 1 plus dgr will be equal to 1 over 1 plus dg multiplied to R. minus G over 1 plus dgw plus dg over 1 plus dgv. So this is the relation for the closed loop system, the error of the closed loop system based on three inputs: reference, V, W, and V. If you want to have a perfect response, how much should be the value in time in the frequency domain, or roughly? What should be the in the DC gain? What should be the ratio of the G1 plus DG? Roughly.
One.
Why 1? If you have a 1, if you put the R, this one equal to 0, R equal to 0, and V equal to 0, so your closed loop error will be exactly as the W, or negative of W. What's the benefit of that, having that one? If we design, look, we can't work with G because G is our plant. And we can change it. Not we can change it, we can make it perfect as much as possible as a passive system. We design the controller when we cannot do anything with the plant or anything more. So I assume G is constant. If I choose or design gain D such that this again is too high, so G over D is a huge value, will be almost 0. So it doesn't matter how much big is the disturbance or how much severe is the disturbance. Because this ratio is 0, the closed loop system will be rejected. The effect of this W on the final response will be almost 0 on the closed loop, error of the closed loop system. The same here. If this ratio is very small, almost 0, so sensor noise won't affect on the overall response of the system. If 1 over 1 plus dg, if the ratio is equal to 1, then I will have exactly R equal to R minus R, error equal to 0. But it's not easy to do that. If you change D such that change W to reject W, it will affect the response of R and V. If you want to reject the noise of the sensors, in order to make this one 0, you will affect the other inputs. How much? You need to evaluate it. There is usually conflict between these three inputs or three objectives. Is that clear? Clear? I know it's all new to you, okay? The only thing that you can help me to make this more, the lecture useful, ask me questions. If anything is unclear to you. Make the module interactive, okay? I don't want to just me talk to you. It's very good for you to ask me your questions. Maybe your question is the question of other students as well.
So you're saying for the coefficient of W, you want that the coefficient to be very small.
The ratio of this transfer function is very small.
Yeah. So that would make W 0, is it?
Not W0. Make the effect of W0.
Sure. So as in a very small value multiplied by W 0.
0. Yeah.
So now for the coefficient of R, you want that to be 1, is it?
1 in the ideal case.
So that your error is equal to R.
No. Will be. Oh, sorry, you're right. Yeah, I made mistakes, guys. I have R minus this one. Yes, if I want to have the error, 1 over 1 plus dg should be almost 0. Yeah, you're right. I'm calculating error. So, if I want to have error between the reference and y equal to 0, this transfer function, its magnitude or its this again should be 0. At the same time, these ratios should be 0 in order to have the perfect system, but it's not the case because there is conflict between them. How does it affect? I will show you.
How do you model a blast transform disturbance? Aren't they usually handled or something like that?
What do you mean?
I don't know. But you got W and P for disturbance, right?
Yep.
What kind of mathematical model do they usually have?
It's a signal. There is no model for it. It's a signal. Can be ramp, can be a step, can be impulse, or
I see.
any kind of. It's a signal. It's not a system. Okay. But we can simplify this ratio by defining the variable S and capital T and looking for sensitivity function S and complementary sensitivity function T. I define sensitivity function S equal to 1 plus over 1 plus dg. And the complementary one as T1 minus S equal to dg 1 plus dg. Why I define S and T such that you will find out later. But just keep in your mind S and T sensitivity function and complementary sensitivity function are defined as this one. If I use substitute S and T in the error of the closed loop system, I will have error of the closed loop system is equal to SR, S is 1 over 1 plus dg, minus SGW plus TV. Okay? Clear, everyone?
That SR does not consider the error at the beginning, right?
No. It's capital S. It's not the small s. It's not the Laplace variable. It's a transfer function. It's transfer function 1 over 1 plus dg.
Okay, but that's all right.
Okay? It's a transfer function. Yeah.
Just now you said the G is can be changed or cannot be changed.
G usually can't be changed
Can be changed.
in the design. We want to change the response of the system by designing proper control system. Okay, so let's discuss what we have said so far. Feedback can reduce the steady state error in response to the disturbances. How the hell it can be happen? Okay, mathematically. In year 2 and so far you said, okay, feedback control system can reject the disturbances. How? Can you prove it? No, I will prove for you now. Okay? So, as a general idea, systems error to constant disturbances can be made smaller with feedback than they are in open loop by factor of S over 1 plus dg, 0, when S goes to 0. Or even you put S is 0, when dg 0 is the loop gain at S equal to 0. If you have, look, the loop gain, keep in your mind, this is important definition. Loop gain is dg, whatever you have in your feed forward path. Or it is dg edge when you don't have the closed loop system. Look, if you look from here, from after the summing point, till behind the summing point is your loop shape or loop gain, which will be dgh in this case. If you have the unity feedback, you will have dg. Okay, this is the loop gain. DC gain or DC loop gain is when S goes to 0, based on the definition of the DC gain. Okay, look, I will explain this one using a practical example. This concept it was investigated by a British engineer almost 100 or 120 years ago when they working on the mining fields and they want to remove the coil from the system, from the mine. they had some problem when they add some load to the train. They couldn't set the speed of the train constant. So they need to somehow remove the effect of the additional load. But in the nowadays, if you look at the cruise system of an automotive, when you go to the up here or if you go to down here, some additional load will be introduced to the system. Correct? Because of the gravity of the Earth. So if I design the control system for the flat road, what's going to happen if I go to the uphill or I go to downhill? Can the system, control system, handle this situation or not? Feedback or open loop?
Open loop.
For sure, open loop cannot because we're saying. But let's see for the closed loop system. For the closed loop system, I can show the dynamic of the engine because we want to keep the rotation of the engine constant. Correct? In order to have the constant speed. So equation of the engine will be G omega dot E plus B omega dot E. Omega is the speed of the engine, angular velocity of the engine, and here is the omega dot is angular acceleration of engine or engine shaft. U is the control input, tau L is the disturbance input. For the simplicity, I assume the reference is 0 in this case, but it's not the case. For sure I have a reference velocity. For example, in the cruise I want to set my reference as a 60 km per hour, or because you are teenage 180 km per hour. Okay? Depends you love speed or not. But anyway, because I have the linear system and I can apply superposition, I remove the reference, but I just consider the feedback signal and disturbance signal. Without loss of generality, you can assume reference is 0. To compare the error, what's the first step? As I said before, the first step of the control design is development of the model. Or to develop the model, you need to build up equations of motion. Here is my equation of motion. Because I have a single system, 1 degree of freedom system, my equation of motion is this. The second step, I need to design the controller. How can I design the controller for this simple case? I need to transfer, or I need to solve my differential equations. How can I solve the differential equation? I need to convert this differential equation to Laplace domain. Let me finish this example, then I will give you 10-minute break. So, as a solution, the Laplace transform will be Sj omega engine plus B omega engine A1 US plus A2 TLS. TLS is the Laplace transform of disturbance. U is the Laplace transform of the control input. Omega is the Laplace transform of the speed engine shaft speed. I reshape the system. I will have the Sj omega E plus B omega. I factor out A1 from here in the second relation. To simplify it more, I will have the S tau omega E plus omega ES plus AUS plus WS. I just factor out B here and define J over D as tau. Here B over B will 1 and A is A1 over B. Okay? So, defining these variables, the final relation will be omega E S is equal to A over tau S plus 1 US plus A over tau S plus 1 WS. Okay? The first order system. Any question? No? Good. So, if I define A over tau S plus 1 equal to GS, US plus WS. If I have open loop system, it means I don't have any closed loop feedback or a closed loop controller. So US will be equal to 0. If I have an open loop system, there is no control action. So So US will be 0. If I put US equal to 0, omega ES will be GS multiplied to WS. What does it mean? So look, before going to the next slide, so keep in your mind the transfer function from the disturbance to shaft engine will be GSWS. Now let's look the closed loop system. If I have a closed loop system and I assume a just constant proportional gain minus K closed U as the minus K closed loop omega E, I assume this is correct. We will talk about how to design K and control feedback in the next lecture. I just substitute U here, minus closed loop omega E. If I reshape this one, I will have omega ES equal to minus GSK closed loop omega ES plus GSW. I just brought this one here, and if you define the variables, you will see what's the omega GS. So 1 plus GK closed loop, this is the control gain, multiplied to omega E will be GW, GSW. And as the closed loop transfer function, omega ES will be equal to J over 1 plus JK closed loop W. To see how the feedback control system will affect the response of the system, I will build up the error of the closed loop system and open loop system from W to Y, the response, to compare how the open loop system works and closed loop system works. So the omega E, the response of the system subject to the disturbance input, will have the transfer function G over 1 plus GK closed loop. But for the open loop system, it was omega E GSW. Let's assume, because I need to have the input, let's assume my input, the disturbance input, is in the form of the S-step input, W0 over S. W0 is a constant value. To calculate the steady state value, I use the final value theorem. If I use the final value theorem, I will get the omega SS equal to G0 W0. Okay? Look at the omega ES for the open loop system is the GSWS. W is W0 over S. This S will be cancelled out with this S. I will have, if I put the S equal to 0, I will have GW DC gain of the G multiplied to W0. Correct? Is it clear to everyone? No? Which part is not clear? Don't say from the beginning. In this slide.
Almost the beginning.
No, I'm talking to you. You said, yeah.
Yeah, from second Y unit.
Here,
Yeah.
look, S tau omega ES plus omega ES equal to A minus K closed loop omega E plus W. Okay? So, A minus A closed loop over S tau. Let me see, make sure that I put it correct way. I will have the GS. Okay, yeah. What if you look at here, I define the GS. Look, GS. Here, A over tau S plus 1 is the GS. I define it here. Okay? So if you look at this relation, if you factor out omega E, will be S tau plus 1. A over S tau plus 1 will be GS. Correct? So the GS is. Yeah.
Y less U is equal to minus KCF times omega.
Because I have the gain in feedback. Look, if I have the K here, KY minus. If I have a control in the feedback. I will explain it, but just assume your control gain is in this form. You don't need to say, no, at the moment you don't need to know why it is in this case. Assume your control law is in this form. Okay. So for the open loop system, I will have G0W. What's the G0? Based on the definition of the GS is A over tau S plus 1. If S goes to 0, G0 will be equal to A. So this one is A, it will be W0. So the open loop system, steady state variation of the omega, or the response of the omega, will be magnified by disturbance. So the open loop system cannot handle the disturbance in any case. But how about, for example, let's say W0 is 1 and G0 is 1. A is equal to 1. In this case, the omega SS will be equal to 1. But my reference is 0, that's right? If my reference is 0, omega SS should be 0. But I have 1. It's a huge difference. Or is 100% error. If you look at here, for the fun, listen to me, for fun I choose K closed loop equal to 99. It can be any value, but for fun I choose K closed loop equal to 99. If I calculate omega SS will be, if I put in the omega, I will have 0.01. Open loop, I will have 100% error. For the closed loop, I will have 1% error due to the disturbance. For example, if I set for the 60 km per hour, if you go to the downhill or uphill, you will get the response. If you go to downhill, for example, we will get the speed of 120 km per hour. If you have a closed loop system, if your target is 60 km per hour, it will be 65 km per hour. So this example shows how a closed loop system can reject disturbances to the system. Is that clear to everyone? How we can get benefit from the closed loop system?
Lower error?
What?
Lower error?
Much lower error. For the open loop, I have 100% error. For the closed loop system, I have 1% error. Okay? 99% improvement in the steady state error. Okay, so the next step, I will talk feedback can reduce the sensitivity of the transfer function to parameter changes. How? I will explain to you after the break, 5 minutes break, because you have 5 minutes break in beginning of the module. Just a moment, please, just a moment.
Getting colder.